So in this section we're now looking at solving differential equations that have y in them. So we're now looking at functions of y instead of functions of x, which we had before. So previously we've seen dy dx equals a function of x, and what you can do with these are a separable type of differential equation, is that you can take this dx, and actually I can pick it up, and put it up onto the right side of the equation. I'll just delete that. And then once you've set your equation up in that way, you can then integrate both sides. Integrating both sides, integrating dy, dy is actually multiplied by 1 if you want to think about it that way. So 1 times dy, if we integrate 1 with respect to y, we get y, and that equals an integral of that original function of x. And that would be our solution to the differential equation. Now this is for a differential equation, like I said, which has this format. So dy dx equals a function of x. We now have x equals a function of y. This is a bit different, because if I pick up the dx component here and put it onto this side and integrate both sides, these variables don't match. So what I need to do is pick up now the function of y and bring that to this side. What that does is it means that we now have the functions of y and the dy on the left side and the function of x on the right. Then what I can do is I can actually integrate both sides of that equation. And I'm just going to write that out a little bit differently so you can see. It's effectively 1 on a function of y, dy, equals the integral of this here. This is really like a 1 lot of dx. So if you integrate 1 with respect to x, you get x. So you get x and the solution for x. And let me just turn this around as well. Put that onto this side. So what we've got here is our solution, which looks very similar, you can see, to the original one up here where we were looking at this dE, which is the more familiar form of differential equation, to this type. So x equals, and instead of an integral just of the function of y, it's 1 over the function of y. Okay. With these as well, generally what you're going to have to do as a final step is to then solve for y as a function of x. That's usually the last step, because the question is given to you in the form of dy dx. Let's do that in red. So dy dx equals a function of y, as opposed to the one up here, which was a function of x. So because whatever's up here, this variable is the y, that's generally what you want your solution to be given in terms of, usually the variable on the top. So I'll just leave that there because that's sort of a nice summary of what we're doing here compared to what we've previously done. So if we have a look at the first one, we've got dy dx equals 2y plus 1, and they've said y has to be greater than -1/2, and that's just because we want this part here, 2y plus 1/2, to be non-zero, and it's because we're going to divide by that function. So let's split this up. So leave the dy there, bring the 2y plus 1 underneath, equals dx. We're then going to integrate both sides. This is a separable equation. And all I'm going to do is I'm going to write a 1 on the top here and put the dy just next to it instead of on top, so it looks like something familiar. And I'm going to put a 1 there as well, so I can see what that will integrate into. We're now going to have x on the right side, and on this side, this is a log, 2y plus 1, but also we have to divide by the derivative of the bracket, which would be 1/2. And as a check here, when you differentiate a log, remember differentiating a log is the derivative of the bracket over itself. And because the derivative is 2, that's why we have to have 1/2 out the front to cancel those 2's and give you the 1 that we started with. And also, I just ran out of room here to put it, we need to put a plus c because we've integrated. Alright, now remember that we're looking here for y because this is dy dx. So now we're going to solve for y. So we now have, let's take the 2 across both sides. So I'm going to have, take the x, the c over with the x as well. So I'm going to have x minus c equals 1/2 log of 2y plus 1. Let's get rid of this side here. So 2 lots of x minus c equals the log of 2y plus 1. Take exponentials of each side. So I should just do exponential there. So we're going to have e raised to the power of 2x minus c equals e to the log of 2y plus 1. I'm actually going to get rid of the modulus signs here because we know that y is bigger than negative a half, so that means that that's going to be always positive. The exponential and the log will cancel, so we end up with e to the power of 2x minus c equals 2y plus 1, and that means we can now solve to get y on its own. Let's move that down a bit. Leave that one there because it's good to see. Take away 1 from the left side. Therefore, y equals a half of e to the 2x plus c minus 1. And that's our solution. So it's the general solution because we have a constant of integration in there as well. What I will show you too at this point, and I'll get rid of this now, is you can do a simplification here, a further simplification. So you could stop at that point, there's nothing wrong with that. What I'm going to do here is just show you, I'll expand everything out. So we have a half e to the 2x plus 2c minus a half. Now this exponential here, from your exponential rules, if you have e to the a plus b, that's the same as e to the a times e to the b. That's one of your exponential rules. So we can use that here to simplify. So if we actually expand this out, we've got e to the 2x and e to the 2c. Now the things that I circle in green are actually constant. A half and e to the 2c, they're both constants. So what we could do here is we could actually rewrite this and call both of those parts a, and e to the 2x is still there, minus a half. And so that's our solution in a simplified form where a equals a half e to the 2c. All you've done is just relabeled a constant as a new thing. I've just called it big A, capital A. So that's a sort of simpler looking solution than the one that's up here. But both of those are completely correct. Okay, so that's the idea with these. It's about inverting and then integrating both sides. So now we'll do the other three there a bit quicker so you can see how they work. Now's a good time to stop the video too if you want to have a go yourself. I'll do these ones quickly. So we've got dy dx equals e to the 2y. Separate it out, bring the x stuff up, and bring the y stuff underneath. We're going to integrate both sides. So we're going to integrate 1 on e to the 2y dy equals the integral of 1 dx. This is e to the negative 2y. So e to the negative 2y integrated is divided by its derivative of the power, and we'll have x on the right side. We're just going to re-express this now. So take away c from both sides. Oops. And then multiply by negative 2. Multiplying by negative, by the way, will just turn these signs around. And the last part here, we can actually take logs of each side, because if we take a log of an e, they'll cancel out. So we have negative 2y equals log 2c minus x. Okay, and to finish off, log negative a half log 2 c minus x. Okay, and that's our general solution. Next one we've got, I'll just do this in a different colour, dark blue. We've got dy dx, this is c, equals the square root of 1 minus y squared, and they've also said that y is only between negative 1 and 1, not inclusive, because that means that we keep this non-zero, and that's important because it will actually end up being a denominator in this question. So we split things up, so we get bring the y stuff underneath, bring the dx up to the right side. I'm going to integrate both sides. I'm just going to put a 1 over the denominator so you can see it more clearly, and integrate the right side and put a 1 there to hold the place in front of the dx. Now if we integrate, hopefully you recognise that this is inverse sine, from your formula sheet. It's inverse sine of y over a squared, over a, and a squared is 1. So it's just y over 1 plus a constant equals x. By the way, if you wanted to, because you're solving for y, it may be advantageous to put the plus c on this side so you don't end up with negative c's everywhere. Not that it makes a difference, but it's just something that you might like to do so you don't end up with negative signs. Okay, so we're going to take the inverse sine, oops, of y, leave that there, x minus c, and now to finish it, I'm going to take the inverse sine over to the other side of the equation where it will become sine of x minus c equals y. And this particular solution now is our solution to the equation. So that's our general solution. Oops. And I might do that just up a little bit. It's our general solution because remember that we've got a constant in there of integration. So therefore, y equals sine of x minus c is our general solution. Okay, so the last one we've got, let's put this on another page, is D, and you may recognise this one too from the 1 minus y squared that we're going to look at here. So we've got dy on dx equals 1 minus y squared, and we've made sure that the 1 minus y squared will never be 0. And we can now split things up. So dx comes up, the 1 minus y squared goes underneath. Integrate both sides. Just going to put a 1 over the denominator to make it look a bit more like something that's easy to integrate. And at this point here, this is something that we haven't really dealt with in much detail. So it's going to be a log, but it is also going to be linked to partial fractions in the sense that it hasn't been something we've seen in much detail because it's got the negative here. We normally see like y squared take away 1, something like that. So I'm going to take a negative out as a factor and then actually flip this around. So now it looks like something we have seen. So for 1 on y squared take away 1, you could use partial fractions for this. Because 1 on y squared minus 1 is equal to a on y plus 1 plus b on y take 1. It's the difference of 2 squares. And then you can go through and find cross multiply here. So 1 equals a of y take 1 plus b of y plus 1. Or you can also use your cas. So if we use the cas, what we can use is the expand command. So I'll do that now, and I'll just shortcut this part here and then finish it off. I've got 1 on y squared minus 1. So in the cas, I'm just going to type expand 1 on y squared minus 1. And it's expanded for you. So it's a half on the y minus 1 and negative a half on y plus 1. So that's what I've just seen in the sheet. And so that means that the negative integral of 1 on y squared minus 1 equals the negative integral of these two things, which equals, this is going to become positive, it'll be a half log y plus 1. This will become negative, a half log of y take 1 plus c, and all of that is equal to x. So that means that x equals, because remember at this point here we knew that this was all x, so on the right side is an x. So we have x equals, I'm just going to put this stuff together now, a half log, this is a y plus 1 over the top of a y take 1. And because we know that y is between negative 1 and 1, we don't really need the modulus signs, so you could just leave that without the modulus signs. So I'll get rid of those. It's guaranteed to be positive. and plus c. So that's sort of halfway to where we want to be. I'm just going to delete this section and finish it off, because remember that we're always wanting to solve for y. So now what we can do is we'll take away c, and I'll also multiply the 2 over as well. So we've just got the log of y plus 1 on y take 1. So that implies that e, raise everything to the power of e, 2x minus c equals e to the log of y plus 1 on y take 1. The e and the log cancel, so then we have y plus 1 on y take 1 equals e to the 2x minus c. Okay. Now this particular equation at this point can be a little bit fiddly to work with, because we now have to do a little bit more algebra. So I'll just get rid of this first part as well. Leave the y plus 1, take the y over, and the minus 1 over as well. So all we've done there, I kind of skipped a step, I might put that step in just so you can see it, is I've just taken y minus 1 up and then multiplied it through. So it's quite fiddly algebra. Take the 1 over and take the y stuff back. Ooh, bit of c in there. And take the 1 over here. Nearly there. Common factor now of y. And a common factor of negative here. So that means that y equals negative e to the 2x minus c plus 1 over 1 minus e to the 2x minus c. If you wanted to as well, because you've got a negative there, what you could do is actually take that through underneath, so you could change the signs underneath, but that's fine the way it is. Okay, to match the solution in your book, by the way, what you'd need to do is go through and do a similar thing that we did for one of the earlier examples, which is a bit of an expansion. So negative e to the 2x times e to the negative c minus 1 over, this would be 1 take e to the 2x, e to the negative c. If you let e to the negative c equal a, we'd then have y equals, this would become, or even negative, make that a. So we'd have positive, so we'd have everything I circle in purple now becomes a. So we'd have a e to the 2x minus 1 on a e to the 2x plus 1, like that. So opposite signs. Okay, so that's the solution that's actually given in your textbook. That's the final solution that they have. And the choices they've made there for A are really just to simplify signs by taking the negative out. But it is really correct at this point here. But this is just an extra step that you can go to simplify your final answer. So with all of these equations, same type of situation, always just inverting so that you end up with the function of y underneath with the dy and integrating both sides. And then the final step, which is to solve for y to give you a final solution. And remember that this here is also a general solution because it has those constants of integration in there. Is the general solution.